All right, we're going to go ahead and get started. Yeah, I know, Matt. We're going to go through new material today, so just sit tight. It's going to be okay. So CPU scheduling, this is actually an incredibly important topic and has a lot of information, so we will be sending, unfortunately, this whole class period staring at these slides. Yeah, I know, I'm sorry. Trying to discuss how CPU scheduling works. I tried to go out and see if I could find a good scheduling simulator out there that we could use as a good lab. I didn't find one, so now you just have to do everything on paper. Yeah, there we go. Yep.
Maybe good.
Maybe good, maybe bad. All right. I love this overview. We're going to learn about scheduling. Thanks. We're going to learn more about scheduling. Okay, thanks. Great. All right, so the idea is we want to, maximum CPU utilization, hopefully we've told, or you've seen, can be obtained using multi-programming, aka running multiple processes at once to try and utilize the CPU as much as possible. But the first thing we need to understand is the idea between CPU burst and I/O burst, and that's a histogram. So, wait, who read chapter 5? No one? No, good. That's what I thought.
The book lies.
What?
The book lies.
The book, yes, we just found out the book is a liar. Oh well. But then you should be used to that, right? Didn't we just have a debate or an election over fake news? Wow, no takers? Wow, that's amazing. No takers. All right, I tried. So CPU burst, what do you think CPU or I/O burst would be? CPU burst. The CPU is bursting.
Using maximum CPU usage in a short period of time.
All right, great. And then I/O burst.
Using maximum input-output.
Yeah, right. So what do you think the relations between these two are?
You can't do both at the same time.
All right. So what does that mean? There's going to be probably a cycle between the two. That's where I'm going. So this is a lovely histogram of a CPU burst. Let's see what we got. The burst durations at the bottom, so how long the burst occurs, and the frequency of the bursts at these durations. So what is this histogram telling you?
There's a lot of bursts that take place around 2 milliseconds.
So most CPU bursts last for
A
short amount of time. Well, 2 milli. In the range of, we'll just say 2 to, 6 milliseconds or something like that. Or 2 to 8 if you really want to cover a lot. Okay.
Most definitely look like between 1 and 4.
Yeah, that's what it looks like from here. Yeah, I like how it was 0. How does that make sense? But we won't go into that. So the point here is that you're kind of alternating between CPU and I/O bursts. CPU burst, wait for I/O, do some more CPU, wait for I/O, do some more CPU, wait for I/O. They're just using burst to basically specify when the CPU is doing either CPU or I/O operations. Ooh, that was a nice double slide. All right, so the CPU scheduler is known as the short-term scheduler. It is what is going to schedule what's on the CPU. So the idea is your program's already in memory. Which program or process, I should say, are we going to put on the CPU, and in what order? What should be the order of the different processes? So let's see. CPU scheduling decision may take place when a process switches from running to waiting, switches from running to ready. Okay. So from running to waiting, that means what does that usually mean?
It's waiting on input.
Yeah, usually it's waiting on input. Running to ready.
Someone
It
else's
was
turn.
interrupted.
It's been interrupted. It's someone else's turn. Right? It needs to take its turn. It needs to share. Switches from waiting to ready.
I/O was received.
I/O was received. Terminates.
It died.
It died. It dead. So then you got to take it off of the scheduler. Why can running the scheduler be beneficial in each of the above? Right, because then the scheduler can figure out what to do next. So scheduling under 1 and 4 is non-preemptive. All other scheduling is preemptive. What does that mean?
I don't know, but I have a feeling you're going to tell us.
Thanks. Yeah, depend on other things, other. Whenever you do that, I always forget the terms in my head because of how you state them.
That's good.
No, it's terrible. No, anyways, right. There's different events that may happen. So switching from running to ready means that you're trying to preempt something else. Something else is coming along the lines, or you're waiting to ready. Woo. Again, preempting. Okay. Not all OSs allow preemption, so they may have to do some non-preemptive scheduler. I think Linux. Well, no, that was with locks.
So those are bold terms. Can you define them?
Those are what?
Bold
terms. They're bold.
Yes.
Very bold terms.
Yeah, I feel threatened by those terms.
You feel threatened by those terms? All right. Well, let's see if we can help you out on the next slide. Not at all. Wow, the slides are really
It's
not.
going to give us a new bold term.
Right, we're going to go with dispatcher.
I prefer italics. They're more friendly.
You want me to change these to italics right now? It'll take forever. All right, so dispatcher module. Let's see. Got me all set up. All right. Gives control of CPU to the process selected for short term. All right, the dispatcher is what does the context switching, jumping to the proper location. The dispatcher, the latency is aka time it takes to stop one process, start another. It's aka how long it takes to do a context switch in total, because it not only has to change the process, but it has to also do some updating to the different schedulers behind the scenes. So the dispatch latency, keep in mind, is the context switch plus whatever else the CPU needs to take care of. All right, here are 5 terms y'all probably should keep in your head for, I don't know, an exam, maybe your homework. Just gonna throw that out there. So scheduling criteria, these are things you want to either, well, pretty much always maximize or minimize depending on the situation. So CPU utilization, do you want to maximize that or minimize that?
Maximum.
Right, because you want your CPUs used as much as possible. Throughput,
Maximum.
maximize. You want to, that can complete their execution per time unit. All right, turnaround time.
Minimize.
Depends on how you look at it.
So the amount of time to execute a particular process. Do you want your process to take a long time or a short time?
Well, you want to take a short.
Right, so we kind of looking to minimize amount of time to, yeah. Waiting time, amount of time process has been waiting in the ready queue. Minimize, because you want that process to be responsive to the user. And the response
time is minimized.
from a request submitted until the first response not output. Yeah, again. Oh, okay, hold on. Amount of time it takes for when a request was submitted until the first response is produced. All right. Are there any questions about these 5? What's wrong with this side of the room?
They're lazy today.
Oh, here we go. Now we're confirming everything we just did. Max, max, min, min, min. All right. So the first scheduling, that may be intuitive. By the way, these lovely numbers right here, the 24, the 3, and the 3 should be over here. Just going to throw that out there. So first come, first serve scheduling. So you have process P1, P2, P3. So first come, P1 takes 24, and then 24 to 27 for P2, and then 27 to 30. Is this preemptive or non-preemptive?
You didn't define preemptive, so I don't know.
You have no idea. It's non-preemptive. Is it preempting these processes with other things? No. They're just running one after another. So what's the wait time for P1? 0, P2,
24.
and then because that's wait till 27. And then has, okay, great, average wait time, beautiful. So if it comes in a different order, the waiting time actually looks a whole lot better. So for waiting time and average, for the waiting time, it depends on when the process comes in to figure out how long it takes before a process can execute. Is this what we want in a scheduler? To have a varying waiting? No, not at all. Shortest job first scheduler. All right. Hey, now we get the two
This
non-preemptive.
sounds horrible.
Shortest job first? Why does it sound horrible? It has a
Because job that takes a
TLA.
really long time might not ever be completed. If jobs that are shorter that keep coming into the queue,
What is that called?
an issue.
Starvation or deadlock. I like that. That's an issue. An incident.
A help desk
A
ticket.
help desk ticket. You all submit it to the help desk and they'll get back to you. Whew. All right. So basically you have to know in the process the length of how much CPU burst, the next CPU burst. Can you actually know that?
Yes. You're defining.
You can define it, true. Will you know that for every process? What are you going to do? Full analysis of the program before it enters the job queue? I'm just saying that data may be hard to decide on, but it is possible. But there is actually ways to do it, and we'll get to that in a moment.
Don't you know how many instructions are in the process?
Or you could take the runtime of a previous execution and associate that with the process as it's running.
What if it's never been executed?
Then you don't know.
But you know the number of lines of code,
Sure.
so you can estimate.
Right, but then that would require scanning the program. So should the kernel be scanning programs before it throws it onto the job scheduler? Ooh, that's a good question.
But it knows how much memory space this takes up.
Sure, but it's not scanning every instruction. It just
It
throws.
doesn't need to, it just scans how much memory it takes up.
Yeah, but what if you have a loop that's from 0 to a bajillion, and the next one is
That's why it's
just.
called an estimate.
It's a terrible, terrible estimate. Okay, two schemes. Non-preemptive, once processed in the CPU, cannot be preempted until it completes its CPU burst, aka I/O blocks it. In other words, nothing's going to stop it. There's no slicing it up. Maybe is a better way to think of it, because it's not going to be preempted by some other process. It has to either terminate or wait for I/O. A new process with a shorter burst in the remaining time of the current, then it will preempt it, aka take it out of the job queue and put the new one in. Does that make a little more sense? I don't trust that smile, Matt. All right, SJF is technically optimal, of course, assuming that context switching has very low cost, because it gives a minimum average waiting time for a given set. The difficulty is knowing the length of the next CPU request. So you're saying maybe we could do code analysis, but that would actually be very expensive. It's an incredibly expensive operation. And it's not an O of 1 operation, is basically what it comes down to. And when you're doing scheduling, you pretty much only want to do O of 1. You don't want to be doing anything extra because that's not the CPU actually doing useful work. It's doing unuseful work, essentially. Oh. All right, again, lovely numbers. This should be over here. So P1 takes till 7. Arrival time and burst. Oh, arrival time and then burst time. This is on non-preemptive. So this is another key piece of information. Is, of course, when you have a schedule, you're not going to get all of your processes at the beginning. Processes come in later after your CPU's been executing for a while. So this first column after the P's is what time it comes in and then the burst time. So 0, of course, is going to execute P1 until it completes. Then it's going to execute P3. Why is it executing P3 instead of P2?
Because it's shorter.
It's shorter. Right. And then at 8, well, notice actually P2, P3, P4 are both in there. Why is it executing P2 instead of P4?
Arrive first.
Because it arrived first. Yep. So average wait time is technically for assuming instant context switching. So preemptive version. Why is P2 jumping onto the scheduler at time index 2?
Because it's shorter
It's shorter.
than the 5 remaining for P1.
Right. So for the 5 remaining in P1, it's shorter, so it gets priority. And then at 4, why do we have P3 jumping on board?
Because 1 is still shorter than 5.
And notice that we had to wait till 4 because that's when the process came in. And wait a second. No, P2 takes 4. That's right. P3 is shorter than the remaining of P3 right here. Mouse pointer.
Shorter than 2.
It's
and
1. P2 at the time is 2. And P1 at the time is 5. So it's shorter than all of them. So he's going to execute. And then why are we going back to P2 at step 5?
Because 2 is shorter than 5.
And shorter than 4, because now you have P4 available. And P4 executes because 4 is less than 5, and then P1 finishes. So average wait time, it says, is 3.
And if we have a million more 1 second P3s, P1 would never complete.
Right. It is terrible. Notice that the execution length was still 16 in both situations, but the average wait time has been reduced. This is just showing why preemptive is helpful.
Isn't that technically false though? What's the overhead for switching?
Right, we are assuming instantaneous switching, which
Doesn't happen.
does not happen. And is a terrible, terrible assumption. But we're trying to just understand preemptive versus non-preemptive.
So basically preemptive means you can stop something in the middle of it.
Right, right. You can stop the process, because in non-preemptive, the process has to say, I'm done. Like, I'm waiting for I/O, or I'm going to terminate. In preemptive, the kernel says, okay, you're done. Get out of there. Yeah. All right, how could we figure out what the burst time is of these processes? Besides doing a full code analysis that would probably take, an n squared, n cubed time or
Are we
something.
assuming they've never been run before?
We can assume they have been.
Then we've stored in some sort of file the amount of time.
All right, there you go. This is actually very common to do. It's called, usually it's called something like exponential averaging. Does it tell you on the next one? No, well that's beautiful. All right.
Oh, it tells you on the next one.
Oh, maybe it does. I'll just keep hitting forward, right? And then we'll just go through all these slides. All right. So Tn, actual length of the CPU burst, aka the most recent one. And T of n plus 1, it would be for the next one. And we got alpha. Alpha is less than from 0 to 1. All right.
And this is for each specific process?
Yes. You would have to keep track of maybe the past 10 or past however many you want. So it would be alpha, should start at 1 here. Oh, that's your weight. What's that?
Fractiony thing.
Fractioning thing. That's your weight. That's how much you want to weight it. So maybe weight it by, I don't know, a half. So the current time plus something previous, maybe not a half, but 0.7, so that you can give more weight to the thing that happened recently and then less weight to what happened in the past. Notice that this is the sum of everything previous. So you actually don't have to keep track of everything, you just have to keep track of the previous t value, and then you're going to update it with some t of n. So this is a kind of a running total or running average. And this is really is just an estimate, but this is very common. You'll see this a lot in operating systems. So hopefully this formula makes a lot of sense. I'll do it again just in case you have any issues. So T of n is the actual length of the last CPU burst. T of n plus, I'll call it tau just because the subscript, that's what it looks like it is. N plus 1, aka what's coming up next and is your predicted value, is what tau of n plus 1 is. Alpha is just some number you want to assign how much weight you want to give the last one versus everything previous or previous. So if you have something close to 1, you're giving the last value more value than everything previous. If you give it close to 0, something else along. It'll be you'll give all the last values more value than the current. So for example, if you made this 0.9, notice in our formula, it'd be 0.9 times T of n, aka the last value, plus 1 minus 0.9, which would make it 0.1 of tau of n, the sum, our previous sum of everything.
I thought that was the predicted for the next.
T plus 1 is predicted value for the next. Tau of n is your sum of everything previous. Any questions? Good. Simple formula. If you actually give it some time, this is kind of what it looks like. Maybe your initial guess was 10, just to give it something. Then you get 6, that might dump it down to 8. Notice as these values come in, it kind of starts to, it's just a curve, basically is what it looks like. It really looks like a curve, but it's giving you just an estimate of what it's predicting the next time is going to be. The black is what the actual time is, the blue is your guess. It's definitely not perfectly accurate, but it generally gives you a good estimation of where of what the next CPU burst is. But the most important thing is, what's the big O of this? 1. And that's the most important aspect of this, because that means it can be calculated quickly.
Where is this stored?
This would be stored in the process PCB, process control board, control. It's stored with the process state inside the scheduler. So it's associated with the process, along with where it is in memory, what resources it has, everything the operating system needs to know and keep track of for the process. So this value would be
Hardware or
stored.
software?
This would be software.
Okay.
Yeah, process state is not stored in hardware at all. Good, exponential averaging. All right, if alpha was 0, then you're pretty much just saying it's the previous, always, which recent history does not count. If it's 1, only the last CPU actually matters. All right, I kind of explained that. That's the formula drug out. It's actually, okay, it doesn't even tell you. Great. But if you put alpha somewhere between, like I said earlier, depending on which you want to give more credit or yeah, credit towards, I guess the best way to put it. You just want alpha between 0 and 1. Down here is just them factoring it all out. But the point is, each of these iterations you would actually calculate every time the process came off the scheduler. All right. Different scheduling for priority. Y'all probably have y'all seen priorities in the OS?
Real-time, normal.
Real-time priority or different priorities?
Yeah.
Yeah.
If you want to make something like run faster or something.
Sure, yeah. Have more time associated with it. You can give it a priority. So it's a number, an integer associated with each process. So instead of this tau, you're just going to give it an integer. The CPU is allocated to the process with the highest priority. Now this is kind of inverted. So the smallest integer is highest priority. So for example, 0 has a higher priority than 100. I guess you could do a preemptive and non-preemptive as well. Shortest job first is actually a priority scheduling, where the priority is predicted over the next CPU burst time, and then it associates the priority. Or you could try and set the priority manually. So what's the problem? What was the problem you predicted so early, Chris?
Starvation.
Starvation, right. So low priority processes may never execute, because if you keep getting high priority processes, you'll never have a chance to do anything. The solution to this is what's called aging, where you slowly increase its priority over time, so eventually it will have a chance to run. I just realized it's using equivalence and not equal right there. Oh yeah. Any other question about priority? It's really just shortest job first, except you set the priority. And you can still do it the same preemptive or non-preemptive way, but you set the priority. So when a process comes in as a higher priority and you're doing preemptive, then you just switch the other process out, put the new one on. And over time, you increase the age or the priority of processes that have not been run. Round robin. How do you think round robin's going to work?
Everybody gets together.
Everybody takes a turn, right? Everyone gets a small unit of time, usually between 10 and 100
Sounds like
milliseconds.
communism.
Communism? Oh, wait, this is definitely communism or socialism in the scheduler world. They're in process? Yeah. The quantum is queued, then each process gets 1 over n. Yeah, so you could set it, or you can actually have the amount of milliseconds be calculated by the number of processes in the queue. So if the queue, let's see, queue time is your quantum time. If the queue is large, it really is just first in, first out. If it's small, let's see, queue must be large with respect to the context switch, because if the queue is below the time for a context switch, then all you're doing is context and switching processes the whole time, which is pointless. Hey, it looks like this. Notice 1, 2, 3, 24, 3, 3, and the quantum here is 4. So P1 executes for 4. P2 only executes for 3. Why does P2 only execute for 3?
That's all we need.
It's all it needed. P3, same thing. And then, hey, look, you're context switching P1 in and out. Okay, obviously the scheduler would know not to do that, but it gets its time slices of 4 from then on out. All right. How about another example? Yep. 1, 2, 3, 4, 1, 2, 3, 4, 1, 3. Oh, the quantum's 20. Okay, that explains it. So 20 there, P2 finishes. P3 still has time left. P4 will still have some more. Then goes back to P1, P3, P4 finishes, then 1, 3, 3. All right.
Why wouldn't you just finish before?
What's that?
I only had 4 left. Why wouldn't you just choose to finish before?
Because communism.
I do not know if I can give you a better answer than that. 20 has been the decided amount, and 20 it shall get. Trying to think of how to integrate, the motherland or something into this, the scheduler land or something. Okay. Yes?
Yeah.
Yeah, I'm looking at this too. I didn't look at this slide before class. So your quantum is 20. Oh, process time 10. There's going to be no context switches. Yes, obviously. If your quantum is 6 and the process time is 10, you'll have 1 context switch. Quantum's 1, you'll have 9 context switches. All right. Just showing you how many context switches you have based on your quantum. So turnaround time, what was turnaround time?
0.
The amount of time the process took.
I forgot too. Let's go back. Wow, these go really slow. Whoa, oh no. All right, back to chapter 5. You got it. Nice. Waiting time, response time, throughput, and utilization. Good job. All right. Wow, it takes almost no time to go forward. All right, turnaround time. So the idea is that it varies with the time quantum. All right. Well, time quantum, and it varies with the process time. The point here is it goes up and down. It's not like there's a, more is exactly better. Although too little is bad because of context switching. So that's why usually 10 to 100 milliseconds, somewhere in that range, is what people use. Why wouldn't you want it to be over 100 milliseconds?
Because then people would start to notice.
Yeah. If you hit a key and it took half a second for it to show up on your screen, people might start noticing that. Okay, so we talked about, well, let me stop the recording.